If you haven't picked up your exam yet, raise your hand. Brett, I know you haven't. Anybody else in here? All right. What I'd like to do today, first of all, Jason, are you ready to do your thing? Yeah? Okay. Sometime in the middle. I want to introduce the notion of arrays, talk about their declaration and syntax, and then do a couple of examples. And then at the end, I'm going to start talking about the cellular automata stuff so that maybe some of you more industrious types can take a hack at it this weekend. So without further ado, let's talk a little bit about arrays and what they're good for. So an array is an indexed collection of variables of a particular type. So up until this point, we've been writing programs with very few variables, 5, 6 variables at the most. That's really not how things are done in computer science. If you go up to Boeing and go into their R&D lab, you will see that there are people there modeling, say, airflow across a wing, and they're solving linear systems with billions of undetermined variables. And when you have billions of undetermined variables, it would be really tedious to make up variable names for all of those. So what you're able to do in every programming language is kind of declare variables in bulk. And that's what we're talking about today. So bulk variables, a big collection of variables of a single type, is called an array. And you can have arrays of 1 dimension, 2 dimensions, as many dimensions as you like. Here's some syntax. So you would, for example, here's an int array A of size 10. Typically what we have here is the data type. And here is just the name, and that follows the standard naming rules. And this is the number of variables. And this is a one-dimensional array. One-dimensional because it's essentially, geometrically, it would be represented by sort of a long row of variables, and you would have the first one, A0, and then you would have A1, A2, etc., all the way down here to A9. Now, what do you notice peculiar about these indices? The first one is 0. The second one is 1. It's just something that you have to get used to in almost all C-based programming languages, and by that I mean C, C++, Java, JavaScript, Python, I think, is even 0 indexed. And this guy is just a normal integer variable. This guy can appear in any context where an integer variable is appropriate. Oops, appropriate. And again, the only thing that you really have to be careful about is this indexing issue, and you'll get used to it fairly quickly. So if you have 10, an array of size 10, the first element is the 0 element, and the last element is the 9th index. 0 to 9, 10 integers. You can also have 2-dimensional arrays. And the syntax there is something like, and let me be consistent here, yes, syntax. The syntax there would be something like int a 10 10. And what this gives you is 100 integer variables arranged in a grid. And that's why we call it a two-dimensional array. So it would geometrically it would look like this. And this guy would be a 0 0, and this guy would be a 0 1, and dot 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 out to a 0 9, and then down here this is a 1 0, all the way down to a 1. Sorry, I'm lying to you. A 1 0, all the way down to a 9 0. Right, there's 10 columns, 10 rows. The first entry is the row number, and the second guy is the column number, row column. And that's just something you have to memorize. That's the way these things work, rows and columns. All right. Now, you guys have already kind of, some of you, go ahead.
Is there a number of dimensions you can use? Is it just 2 dimensions?
I can go on and have a 3-dimensional, 4-dimensional. I will say that in this class we'll never use more than a 2-dimensional array. 3-dimensional arrays are really rare. I can't think of a single example where I've used one or where I've even encountered one. That doesn't mean that they're not out there, and certainly the syntax supports as many dimensions as you like, as many indices as you like, but 1 and 2 are by far the most common. All right. What are the limitations here? You can make this thing as big as you want. You do have to be careful. There's 100 integer variables. Does anybody remember how many bytes a single int takes?
8, 4.
Close. 4. So to declare this array takes how many bytes? Four bytes per int. 100 ints. 400, yeah. My point is, it's really easy to, with large arrays, to suck up all the memory in your computer. So you have to be extremely careful. That said, 400 bytes is no problem for modern computers. But doesn't take long, right? If you do like a 100 by 100, now you're at 10,000 integers. That's 40,000 bytes. Let's do 1,000 by 1,000, 1,000,000 by 1,000,000. Then you start talking about real memory. So, as I mentioned, some of you have used strings in your programs. Not everyone, but a string is something that was introduced way back in Chapter 1 or Chapter 2. Do you remember what a string is?
Multiple characters.
Yeah, it's a collection of characters. What would a string be used for?
Like a word.
Yeah, to store a word or a phrase. A string is secretly an array of characters. And to that end, and to try to sort of bring home this idea of what you can do with arrays, I'm going to play around with strings a little bit. So I'm going to do an example where I'm going to read a string from the user, and I'm going to print it back to the user in reverse. Really simple example to reverse a string. So let's switch over to the terminal here and write this program really quickly so you get an idea of how strings work in an actual, or sorry, how arrays work in an actual program. Do you remember what I have to do if I want to play around with strings? Yeah. So it's not part of the default set of data types, but if you include string, then this provides access. All right. Bless you. So we now have string data types. Let me declare a string, call it S, and I'm going to ask for the string. Bless you again. This is a new command, possibly. This will read up to the \n, including spaces, into S. And let me just make sure I have the syntax right. It may have to be reversed. Nope, it's good. Okay, I now have the string sitting in S. Just to show you that it's working, I'll print the string out. And what's nice about this is I can do a sentence or a phrase. And it grabs the whole thing all the way up to the end and puts it in the string. Spaces and everything. Punctuation, all of that. How is that string represented in the computer, in the running program? It's represented as, hold on for a second here. It's represented as an array of characters, as I mentioned earlier. And the way it works is, here is the array of characters. We don't really know exactly how long it is, but you know, it's maybe 20 or 30 characters long. It's at least 26 characters long. The first character in the character array is capital T, and it's sitting in the 0 index slot. And then H is in the 1 index, E is in the 2 index, there's a space character in the 3 index, etc. In fact, we can talk about how long it is. It's 45 characters long. So I can actually ask the string, how long are you? And it'll tell me with this .length command. I can print out the first character in the string. Come on. Using array index notation. S left square bracket 0 right square bracket is the first character in this array. Let's see what that looks like. Okay, now here's the real power of arrays. It's not that I can pick out particular pieces, it's that I can manipulate the things in the array algorithmically using loops and so forth. Let me show you what I mean by that. Let's do a for loop here. For int I equals, let's do s dot, let's do 0 up to I. I'll put a space in between every character. So how is this going to work? Here's my for loop. I start out with index I 0, and I go up to index I the length of the string minus 1. I'll talk about why it's the length of the string minus 1 in a second. And what I'm going to do every time is just going to print out SI. What is SI? It's the ith element in this string of characters. It's going to start out as 0, S1, S2, all the way up to S length minus 1. All right, let's see what that looks like. So I now have a systematic way of manipulating the elements of this array, playing around with the elements of this array. Nice. You could just not answer it. All right. Now, what if I want to print this thing in reverse, which is what I initially set out to do? Ideas. Carter.
I equal the length, and then you have it go down instead of up.
Sure, I could do that, or I could do. Let's do that. Is this going to work? There's one tiny problem.
It should be S length minus 1.
It should be S length minus 1. Why is that? It's partly, you guys have to know what length is. Length is the number of characters in the string. So there are 45 characters in this string, which means the index goes from what to what? 0 to 44. 0 to 44. So if I want to reverse it, I need to go 44 down to 0. The length is 45, so let's fix that. Oh, and I'm going to get rid of the space too. Whatever that is. Yeah, it's like listening to Led Zeppelin albums backwards or something. I don't know, but you can read whatever you want into that. Yes. There are other things that you could do. For example, we could get rid of the spaces if S. How would we get rid of the spaces? I'll let you tell me. Yeah, so let's do it the other way. Let's do if Si is not equal to a space, print it out. Okay, and I'm going to go back to the other way just for a bit. Whoops. Line 20. Oh, thank you. So there's a way of filtering that string and removing things that you don't want. There's lots of things you could do. You could, presumably, if I gave you guys enough time, you could perhaps change all the letters to uppercase. Their uppercase equivalents. Maybe you could think about how you might do that. Or you could change all the letters to lowercase. When you see applications that do this kind of thing, that's what they're doing. They're manipulating the character array that underlies the string. The thing about arrays is this is a very powerful way of manipulating data now. I don't really have to talk about S0 and S10. I can talk about SI, and I can move I around. therein lies the real power of arrays, both 1D, 2D, and higher, is the systematic access and writing of the data. One last thing. Let's pretend that I really did want to change that first character to lowercase. I'm just going to use the same example for the sake of time, but I could do something like this as well. S0 equals T. And I'll get rid of the space filter. What's going to happen if I do this? Do you think? Bless you. It's going to take the capital T in that example that I've been repeatedly using and turn it into a lowercase t. So it's going to take that character T and put it in the first slot of the string. In other words, overwrite the first character in the string. So let's do that really quickly. So what did I enter? I entered the sentence with a capital T. What got printed out after we showed you what the first character was, what was printed out was the lowercase version. I essentially overwrote that one character, that one slot in the array with another value, and I could overwrite it with anything, obviously. Something that doesn't make sense, for example, and rerun it. Whoops. Oh, come on. There we go. I can put whatever I want in there, as long as it's a character. Questions about that? All right, Jason, come on up and tell us about Mozilla. Do you need a web page?
Yeah, to my email.
Do you need Mozilla?
No.
I actually have it installed if you have it. So. While he's pulling that up, I'm in chapter 7 now, and I've assigned sections 7.1 and 7.2. And as always, I'm giving you the disclaimer that I am not presenting nearly everything that is in those two sections. So you do need to go home and read those if you haven't done so already. You ready?
Just about. 1 sec.
No, I'm just leaving it in there. If you want it,
Alrighty.
let me know and I'll take it out. You ready?
Yeah.
Go.
All right. So I'm gonna talk about Mozilla. I guess I'll start out by telling you what it is, and then I'll tell you kind of how it came to be, an important story that goes along with it. So Mozilla is one of the largest open source software projects, and it was started in 1998. And what this project did was it created an open source code for web browsers. And so it's licensed to grant users the right to use, copy, study, change, and improve its design. So this code is just available online. You can literally find it on the internet. And the whole idea of open source is that anyone can contribute ideas to it and make improvements to it. And the primary language that's used in this open source code is C and C++. I think there's also aspects of JavaScript in there as well. And it contains millions and millions and millions of lines, as you would expect. It's pretty complicated code. So the story of Mozilla is that kind of previous to the 90s, and I guess in the 90s as well, companies would always put patent on their software. If you had a code that was yours and you weren't going to let anyone else look at that code because you wanted to reap the benefits of that. So yeah, intellectual property was rarely released. But as I'll talk about later, Mozilla kind of changed the view of this. And the birth of it can date, it dates back to Mosaic, which was one of the first web browsers and is credited with popularizing the World Wide Web. And eventually, Mosaic turned into Netscape, and I think Netscape was the leading web browser when it came out. But once Microsoft kind of saw what was going on, they decided to jump on board, and they created IE. If you guys remember that from back in the early 2000s, and they coupled IE with their operating system, so they came as a package, and they kind of drove Netscape out of business. They kind of took over that industry, and so kind of in response to it, the Mozilla project began in 1998, and the leaders of this project came up with the idea of not keeping this code, their code, just to themselves. They opened it up to the industry, and they had a whole bunch of developers working on this code, and it started out as Netscape's code, but it was Netscape's code under the Mozilla project. And so what this did was that they were able to make a lot of improvements really quickly, because it wasn't just people in their corporation working on the code. It was a bunch of different developers, a bunch of different people, and they could solve bugs much more quickly and just make improvements faster. So they actually eventually IE was not able to keep up with that, and the reason that we see Firefox, why you kind of see Firefox in association with Mozilla, is that it was created as a standalone browser with Mozilla, and it uses that code. So I guess just to sum it up, the Mozilla project was just a pretty revolutionary and radical idea, because they made their code available to everybody. And today, a lot of browsers use this idea. Chrome also uses open source code. So, any questions? Yeah.
Has IE started using open source?
I don't know, actually. I don't even know if IE is around anymore.
Oh yeah, and
Yeah.
the short answer is no.
Okay.
Other questions?
Yeah.
So Mozilla isn't just Firefox?
No, well, yeah, because I know it's kind of confusing because you associate those things together. But yeah, it was the project of this open source code that they started. And Firefox is actually the browser, the web browser.
So rather than thinking of code, what was the code? I usually think of code as being aimed at producing a particular program.
Mm-hmm.
But the program that was aimed for wasn't specifically Firefox, and what was it?
Well, it's just a web browser. Yeah.
There are other browsers out there much less popular that are based on the Mozilla code base,
Mm-hmm.
but Firefox is a particular packaging and rendering of that code, of the Mozilla code, that in fact the Mozilla Foundation supports. But there are other people that can go in and download that code base and then tweak it on their own and make a different browser if they want. Maybe you're a mobile phone developer and you need a browser. You can go to Mozilla and download that and tweak it and make it work on your phone. You can't call it Firefox because that's trademarked by Mozilla. Even though it's free, the name is trademarked as being the result of this particular process. But you can still use Mozilla's code base to make your own browser. Okay, thanks, Jason. Alrighty. It's probably the second biggest open source project at the time. The largest open source project at the time was likely, I don't know if you want to lump all of the Linux stuff together into one project, but that would be sort of misleading. But certainly the Linux kernel was one of the biggest open source projects at the time. So they didn't invent going open source. They went open source essentially because Microsoft destroyed their business model. They had nothing left to do, and they figured we'll just give the code away. and see what people do with it. And that's where Firefox came from, essentially. All right, let's go and talk a little bit about the cellular automata program. Let me close that. And let's go here and here. All right, and I want to talk a little bit about binary numbers, binary expansions. You'll not be surprised to know that to calculate cellular automata, at least this kind of cellular automata, it's really important that you understand binary numbers, how to take a number and represent it in binary notation. So what I'd like to start off with for 5 minutes or so is just to remind everybody or show everybody how to take a number and represent it in binary. Binary is really just base 2, and maybe back in middle school or high school even, you learned a little bit about representing numbers in different bases, base 8, base 10, all that sort of stuff. Binary is just base 2. In base 10, you have 10 digits available to you, 10 symbols for digits available to you, the digits 0 through 9. In base 2, you have 2 digits available to you, 0 and 1. Okay, binary is really just base 2. And let's compare to base 10. So if I write down the number 213, we know how to expand that. We've memorized what the place values are in decimal notation. So that's 2 times 10 squared plus 1 times 10 to the first plus 3 times 10 to the 0. Is that familiar to everybody? So this is the least significant digit, and this is the most significant. Least significant because that digit corresponds to the 10 to the 0's place, and most significant because that refers to the 10 squared place, and 10 squared is more significant. It's a bigger number than 10 to the 0. That's it. And so we list the least significant digit on the right, and we go in increasing significance till we end at the left. Base 2 is exactly the same. So in base 2, we go from left to right. And that's most to least significant. And the way it'll work, let's say we have an 8-bit binary number. Then what we have is 2 to the 7th, 2 to the 6th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st, 2 to the 0. Those are the place values. And the digits that are available to us, as I've already mentioned, are just 0 and 1. So every binary number is going to look like just a list of zeros and ones in some particular order. So I'll just kind of randomly fill this in. So I just randomly laid down some zeros and ones. This is a binary number. How do we interpret this? We see that this is 1 times 2 to the 5th plus 1 times 2 to the 4th plus 1 times 2 squared plus 1 times 2 to the 0. And if we want to figure out what number that represents, we have to do the arithmetic there. So it's, 32 plus 16 plus 4 plus 1. And if we add that up, we get, 48, 52, 53. And we're just so used to thinking in base 10 that we write 53 automatically. But remember that the integer 53, it's not a real physical thing, but it's a thing that's independent of base. Right? 53 is 53 whether you're in binary or decimal or whatever, right? What does 53 mean? What does 2 mean? Really? Come on. You can do it. What does 1 mean? I know, it's not getting any easier, right?
Yeah. Still stuck in the metaphysical implications of this.
Yeah, don't think that hard. 2 means 2 things.
Okay, so 53 is
53 means 53 things. And 53 things,
That's not an answer. It's just
53 things are going to still be 53 things, whether you represent them in binary, decimal, octal, hexadecimal, whatever. It's still going to be 53 things. So what does 53 mean? It means there's 53 things there. Even the word 53, what base am I using? 10. But if you peel away the base, there's still some meaning there. It's 53 things, 53 discrete somethings. All right, yes, there are deep metaphysical implications to what do numbers actually mean, but that's not where I'm headed. All right, so here is your standard way of representing an 8-bit binary number. What do I mean by 8 bits? What's 8 in this context?
How many places you
How many slots I have, right? So I could talk about 10-bit binary numbers or 20-bit binary numbers or no-bit binary numbers. No, I couldn't, but
isn't 8 bits also a byte?
it is, and that's why I used 8, because we're going to be talking a lot about bytes. What's the biggest, in this representation, what's the biggest number that I could represent? What's the biggest number of things that I could represent?
256. Whatever 2 to the 7th times.
Yeah, the biggest, the most number of different configurations here is 2 to the 8th, which is 256.
But the biggest number isn't 2 to the 7th times 2 to the 7th.
Right, the biggest number is 255. The smallest number is 0. But it has 256 different configurations, this collection of bits. So the range here is from 0 to 255. All right. How hard would it be to write a program to convert a number to binary? Let's do that. Let's pop over to the example directory here. I'll leave this mess for you to look at later. Let's say decimal binary convert. All right, so I'm going to convert this guy to its binary digits. I'm going to have a look at its binary digits. In fact, let's let's focus on 53 since we kind of know what this should look like. Right, 0, 0, 1, 1, 0, 1, 0, 1. Here's a nice little recipe. Does anybody know how to do this before I give it away? From decimal to binary. So let's say I put in 53. Can you tell me how to get this collection of zeros and ones? Okay, so that's going to get me, you're absolutely right, that's going to get me the first digit. How do I get the next one?
Wouldn't you divide by 4? Like, you divide by the...
Say again?
You want to take the remainder.
Right, so remainder by 2, which, and then what?
See the next one.
What is the next one? So where do I go after that? So here, let's
So, like, see if you can divide by 2 to the 7. Like, the 0. And then
yeah,
see if
you
divide
could
by
do that.
2. I mean, that's
Here's what I want to. If this thing is an odd number, what do we know about its least significant digit?
it's 1.
It's 1. Otherwise, it's 0. Okay. What would happen to this guy, this whole thing, if I divide it by 2? Well, think about what happens when you divide a decimal representation by 10. What happens to it? The decimal point moves over 1, right? The same thing happens in binary. If I divide by 2, what happens is I move the decimal point over. If that's odd or even, 0 or 1, then what? Move the decimal point over again. So what you keep doing is n%2, n divided by 2. n%2, n divided by 2. n%2, n divided by 2. Let me show you that. So I'll do 8. Sure. n/equals 2. What does that mean? It's the same as n equals n/2. So it's taking n and it's overwriting with the half of n. Oops. Wait, did I do that? No, I didn't. Let me get that in there. Okay, so what's one that we know? We know 53. Okay, let's compare. What do you notice? It's backwards. Yes. That's annoying, because what I'd like to do is print most significant first down to least significant, because that's the convention. Ideas on how to fix that?
strings. Maybe like put it
Close. Not quite strings. Arrays, yay.
Sorry.
Okay, so how might we do this with an array?
Have like an array, a one-dimensional array of 8.
Yep, I like that. So let's declare that at the top. Now what? I'd like to reverse these guys. So I have an array to hold each digit. What should I do first before I try to print these things out?
Make each.
I should store these bits in the array. And then once I'm done, then I can do whatever I want with the array. So let's do that instead. So how might I store this information? Rather than printing it out right away, Let's store it in the array and then print it out. So how should I modify this for loop first? Yes. So now, where is the least significant binary digit? Which slot in the array? R0, right? And then R1 is the next least significant, all the way up to where is the most significant bit? R8, R7 actually, R7, 0 to 7. So when I'm done, what I have is an array that's populated with the least significant bit down in R0 and the most significant bit up there in R7. Now, I'd like to print this thing out in reverse. Oops, I have to leave that in there. I'm going to put it the old-fashioned way. There. I still have to do that so that I can slide the decimal point across. Now I'd like to print this thing out in reverse so that I can get the representation that I want. How might I do that?
We can count backwards.
Yeah, go ahead, Danielle. This guy doesn't have length because unlike a string, this is just an integer array. It'd be nice if it had length, but we actually know its length. It's 8. So go ahead.
So would you do like 4, 8, I equals 7?
Yes. See out what? And just for good measure, after I'm all done and printed all the digits, I'm going to print a carriage return. Let's see what that does. So a two-step process. I get the digits first, then I print them out in the order that I'd like. Why do I care about this? Let's go back to the cellular automata thing in closing here. This guy is an 8-bit binary number. 0, 0, 0, 1, 1, 1, 1, 0. Without reading ahead, what binary number is that? Can you do it in your head? So this is 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th. 32 plus 16. I'm sorry, did I say that one off? 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th. 16 plus. It's 30, yes. That's 30. Let me, in fact, verify that. I'll run it again. 0, 0, 0, 4 ones and a 0. 0, 0, 0, 4 ones and a 0. What we're starting to see here is the correspondence between the rule number and the rule. How do you generate the rule? You get the rule number and you compute its binary digits and you store them in an array. In our program, this array of numbers is called what? It's R. It's the array R. All right, so we're good. Now, it gets even better. So now we know how to represent numbers between 0 and 255. Those are all the rules that were allowed. 0 to 255. Nothing, no negative rules, no rules higher than 255. That's all you're asked to handle. And what we see is every number, every integer can be represented in the array R using this little recipe. I can store it in R. Here's where it gets interesting. Let's say I'm at a particular cell and I look at the 3 cells above. And we can look at them and we know they're either alive or dead. Here's where it gets really cool. Treat these triples as little 3-bit binary numbers. Here's a 3-bit binary number. What binary number is it? This is least significant up to most significant. That's 1. What index in R is that? It's also 1. How about this guy here? What 3-bit binary number is that? It's 5. It's 5. And what array index in R is this guy? 0, 1, 2, 3, 4, 5. So these little triples of boxes are really just binary array indices, 0 to 7. Right? This guy up here, 2 to the 0 plus 2 squared plus 2 cubed is 7. So I'm sitting here at a cell, and I know that the 3 cells above look like this. And I want to know whether I should make it alive or make it dead. Well, this turns into a 6, right? I go to the array R, and if the 6th slot is a 1, I bring the cell to life. And if the 6th slot is a 0, I make it dead. I'll talk more about this on Monday. Think about that.